Imagine a world with clouds, rain, rivers, lakes, seas, dunes, weather, and an atmosphere thicker than Earth's. Now imagine that every single one of those familiar features is made from the wrong chemistry, at the wrong temperature, under a sky so cold that your blood would freeze solid in seconds. That world is real. It orbits Saturn right now. Cassini saw it. Huygens landed on it. And from the surface, it looks almost like somewhere you could live until you realize the rain is liquid methane. The rocks are frozen water. The air has no oxygen. The lakes would kill you faster than falling into Arctic water. And the nearest help is more than an hour away at the speed of light. This is what living on Titan would actually feel like. If you enjoy stories that make you rethink what survival really means on other worlds, hit that like button and subscribe. Now settle in and get yourself comfortable. Let's begin. On January 14th, 2005, a small metal disc the size of a kitchen table dropped through an alien sky and changed everything we thought we knew about what a moon could be. The European Space Agency's Huygens probe had separated from its mothership, the Cassini orbiter, 3 weeks earlier, and had been coasting alone through the void towards Saturn's largest moon. Now it was falling. For 2 hours and 27 minutes it descended through thick, orange haze, slowed by parachutes and buffeted by super-rotating winds that reached speeds of more than 400 kilometers per hour in the upper atmosphere before gradually slowing to a whisper near the surface. Those winds roared loud enough for Huygens' onboard microphone to record them. The recording became the first natural sound ever captured from the surface of another world in the outer solar system, not a beep from an instrument, not a synthetic tone, but the actual, unfiltered voice of an alien atmosphere rushing past a descending spacecraft. And what Huygens heard, saw, and measured on the way down was not what anyone had expected. The cameras revealed drainage channels cutting across a highland plateau, branching, forking, converging the same dendritic pattern you see carved into mountainsides on Earth wherever water flows downhill. Dark, flat lowlands stretched beyond the channels, looking eerily like a muddy coastal plain seen from the window of a descending airplane. Scientists watching the images arrive, delayed by more than an hour because of the vast distance the signal had to cross, saw what looked unmistakably like a shoreline. A boundary between lighter, elevated terrain and a darker, smooth expanse that seemed to have been recently wet. When Huygens finally struck the surface at a gentle walking pace, it did not crash through ice or sink into liquid. It landed on something with the consistency of wet sand or loosely packed clay, compressing the ground by about 12 centimeters before settling. A brief burst of methane gas rose from the impact site, as though the ground had exhaled, as though the soil beneath the probe was saturated with volatile hydrocarbons just below the surface, and the impact had released a small pocket into the frigid air. The surface temperature registered at minus 179 degrees Celsius, and yet the landscape in every direction looked like a cold, overcast beach after a heavy rainstorm. Rounded pebbles sat scattered across a flat plain, varying in size from a few centimeters to roughly 15 centimeters across. They were not rock, they were water ice, frozen so hard at that temperature that they behaved like cobblestones. The dark material coating the ground between and around them was not soil in any biological sense. It was a layer of complex organic compounds, a residue of photochemistry performed in the upper atmosphere over millions of years, drifting down particle by particle to blanket the surface in a thin but persistent coating of hydrocarbon sludge. Everything Huygens was looking at had a direct visual equivalent on Earth, and every single one of those equivalents was made from the wrong material, at the wrong temperature, under a sky that no human could survive breathing for even a few seconds. For 72 minutes, Huygens sat there on that frozen surface, transmitting everything its instruments could measure back to Cassini passing overhead. The temperature sensor confirmed what models had predicted. The surface sat at conditions where methane can exist as both a liquid and a gas, simultaneously condensing into pools and evaporating back into the atmosphere, just as water does on Earth. Our planet sits near conditions where water can cycle between liquid, ice, and vapor. Titan sits near the equivalent threshold for methane. This is not a coincidence of naming. It is the fundamental physical reason why Titan has a methane weather cycle at all, and it is the single most important fact about the Moon's surface environment. On Earth, water drives everything. On Titan, methane does. Same thermodynamic principle. Completely different molecule. Completely different consequences for anything alive. That landing was the beginning of a realization that has only deepened in the 2 decades since. Titan is not merely another icy moon among the hundreds that orbit the gas giants of our solar system. It is the most deceptive world we have ever discovered. It is the place that looks most like somewhere you could imagine living, while quietly being one of the most chemically hostile environments a human being could ever set foot on. And the danger does not come from what is obviously alien about it. The danger comes from what looks almost right. Start with the atmosphere. Titan is the only moon in the entire solar system with an atmosphere worth mentioning. Not a thin wisp of trace gases clinging desperately to a rocky surface, like what you find on some of Jupiter's moons or at the margins of detection on Earth's own moon. A real, substantial, opaque atmosphere, thicker than Earth's, taller than Earth's. Titan's atmosphere extends roughly 10 times higher than ours, nearly 600 kilometers into space, because the moon's gravity is weaker and cannot hold the gas as tightly. But at the surface, the atmospheric pressure is approximately 1.5 bars, about 50% higher than the sea level pressure you are experiencing right now. If you could somehow survive the temperature long enough to notice, you would feel slightly more atmospheric weight pressing against your body than you do sitting in your living room. NASA has compared it to the pressure you would feel swimming, about 15 meters below the surface of an ocean on Earth. It is firm, tangible, undeniable. You would feel Titan's air against your skin the way you feel a heavy, humid day pressing down on you in summer. In terms of pressure alone, Titan is more comfortable than Mars, more comfortable than the Moon, more comfortable than any other solid surface anywhere in the outer solar system. On Mars, the atmospheric pressure is less than 1% of Earth, so low that your blood would boil at body temperature if you were exposed to it unprotected. On the Moon, there is essentially no pressure at all. On Europa, nothing. On Ganymede, nothing that matters. On Titan, you do not need a pressurized suit to keep your body from catastrophically decompressing. The air pushes against you at a level your circulatory system, your lungs, your eardrums can handle without mechanical assistance. This is the first part of the illusion, and it is a powerful one, because atmospheric pressure is one of the primary engineering constraints for every spacesuit and habitat ever designed for any world beyond Earth. Removing that constraint sounds like a gift from nature. It sounds like Titan is doing you a tremendous favor. It sounds like the hardest part of surviving on another world just got easier by an order of magnitude. It did not, because the atmosphere that provides that convenient human-compatible pressure is approximately 95% molecular nitrogen and 5% methane, with traces of hydrogen and a menagerie of complex hydrocarbon and nitrile compounds. There is zero free oxygen. Not a dangerously reduced level of oxygen. Not a thin trace you could supplement with a concentrator. Absolutely none. A human being taking a single unprotected breath of Titan's atmosphere would inhale nothing that their lungs could use. Consciousness would begin to fade within about 15 seconds. Brain damage would follow within 4 minutes. Death would come shortly after, not from poison, not from pressure trauma, but from the simple, silent absence of the one molecule your body cannot function without. You would suffocate standing in an atmosphere denser than Earth's, surrounded by more air molecules pressing against your skin than you could possibly need in terms of volume and pressure. The quantity is generous, the chemistry is lethal, and the feeling of adequate pressure against your body would make the death even more disorienting, because every instinct you have associates that feeling with being able to breathe. Now look up. From the surface, Titan's sky is a deep, smoky orange fading to brown near the horizon. The color is not caused by dust or by water vapor or by anything you would recognize from an earthly sunset. It comes from the haze, and the haze on Titan is not fog. It is not cloud in any way that you understand cloud. It is a permanent, planet-wide photochemical smog layer produced continuously in the upper atmosphere. Ultraviolet sunlight and high-energy particles accelerated by Saturn's magnetosphere slam into methane and nitrogen molecules hundreds of kilometers above the surface, breaking them apart. The fragments recombine into increasingly complex organic molecules: acetylene, ethylene, hydrogen cyanide, benzene, and eventually very large heavy molecular chains called tholins. These tholins are not a single compound. They are a broad family of reddish-brown organic polymers that do not exist naturally anywhere on Earth. They are unique products of a nitrogen-methane atmosphere exposed to ultraviolet radiation over geological time, and they drift downward through the atmosphere over weeks and months, forming the thick orange blanket that gives Titan its signature color from space and plunging the surface into permanent gloom. This haze has a consequence that matters enormously for any discussion of survival. It blocks sunlight with extraordinary efficiency. Titan orbits Saturn at an average distance of roughly 1.4 billion kilometers from the Sun. At that distance, sunlight reaching the top of Titan's atmosphere is already only about 1% of the intensity that hits the top of Earth's atmosphere. 1% is already very little, but the haze absorbs and scatters the overwhelming majority of even that meager light before it can reach the ground. By the time photons filter through the full depth of the haze layer and reach the surface, Titan receives roughly 0.1% of the solar energy that bathes Earth's surface. Some researchers have compared the illumination level to late civil twilight on Earth, that narrow interval just after sunset when the sky has gone grey, colours have bled away, and you can barely read large print held at arm's length. Others have compared it to the light level deep inside a thick forest on a heavily overcast day. Either way, the surface of Titan at local noon is darker than almost any naturally occurring outdoor environment on Earth. This means solar panels are effectively useless for any serious power generation. A solar array on Titan would produce less than 1,000th of the electricity it would generate on Earth. A panel that powers a house on Earth would barely charge a flashlight on Titan. Any habitat, vehicle, rover, or life support system operating on the surface must be powered by something that does not depend on sunlight. Nuclear energy is the only realistic option. Specifically, radioisotope thermoelectric generators, the same kind of compact nuclear heat sources that have powered Voyager, Curiosity, and Perseverance for years and decades at a stretch. NASA's Dragonfly rotorcraft, currently being assembled at the Johns Hopkins Applied Physics Laboratory for a July 2028 launch, will carry a multi-mission radioisotope thermoelectric generator, the same basic type used by Curiosity and Perseverance on Mars, because there is simply nothing else that works. There is no alternative. The sun cannot help you on Titan. The weak light also means that any human on the surface would exist in a permanent state of visual deprivation. There would be no sunrise, no sunset, no bright daylight hour to orient your circadian rhythm. The sky would shift from marginally brighter amber during the day to deeper brown-black at night, but the difference would be subtle. Human beings who spend extended periods in low-light environments experience measurable psychological effects: disrupted sleep cycles, depressed mood, impaired concentration. On Titan, this would not be a temporary inconvenience. It would be a permanent condition. Every day would look like a dim, cloudy twilight, and it would never end. Now layer in the cold: minus 179 degrees Celsius, minus 290 degrees Fahrenheit, 94 Kelvin. These numbers are so far outside the range of human experience that they lose meaning the moment you hear them. For comparison, the coldest temperature ever recorded on Earth's surface at Vostok Station in Antarctica in 1983 was minus 89.2 degrees Celsius. Titan's surface is almost exactly twice as cold as the most extreme cold any place on Earth has ever experienced. The lowest temperature a human being has ever survived outdoors, even briefly and with extreme cold weather gear, is roughly minus 70 degrees Celsius. Titan's surface is more than 100 degrees colder than that. This is not a hostile winter. This is not polar expedition cold. This is a regime where the concept of cold as humans understand it stops being useful, because nothing in your evolutionary history or your engineering history has prepared you for it. So consider what this temperature actually does. At this temperature, water ice behaves like granite. It does not crack under mild pressure. It does not feel slippery. It does not melt or deform or sublimate at any rate you would notice. It is structural material bedrock: boulders, pebbles, gravel. The surface of Titan is made of water ice bedrock coated in hydrocarbon sediment. When Huygens photographed those rounded pebbles at its landing site, they were water ice that had been tumbled smooth by flowing liquid methane, in the same way river stones on Earth are polished by flowing water over centuries. At this temperature, carbon dioxide is a solid. Oxygen would be a liquid if it existed there in any quantity. And methane, the gas that heats your home, the gas you smell when a stove burner clicks before it lights, is a liquid. It pools, it flows, it fills enormous basins and sits there under the dim orange sky, placid and transparent, forming lakes and rivers and seas. Cassini spent 13 years orbiting Saturn and completed 127 targeted close flybys of Titan during that time. Its synthetic aperture radar cut through the haze that defeated optical cameras and mapped the surface beneath in remarkable detail. What it revealed was a world with geography that reads like a funhouse mirror reflection of Earth. In the northern polar region, 3 major seas dominate the landscape. Kraken Mare is the largest its surface area, roughly comparable to the Black Sea on Earth, with radar-derived depth measurements suggesting hundreds of meters of liquid methane and ethane in its deepest sections. Scientists estimate it may hold roughly 80% of all the surface liquid on Titan. Ligiu Mare, the second largest body, turned out during detailed analysis of Cassini radar data to be filled with nearly pure liquid methane, with a seabed coated in a sludge of organic-rich material. Punga Mare sits nearby, elongated and complex in shoreline shape. Surrounding these seas are dozens of smaller lakes, some deep, steep-sided depressions that appear to have formed through dissolution or collapse of the underlying terrain, resembling nothing so much as karst sinkholes and dew lines formed in limestone country on Earth. In the southern hemisphere, a solitary lake called Ontario La Cruz sits alone, roughly the size of its terrestrial namesake. Its composition measured as a mixture of methane and ethane. These are real seas with real physical properties that scientists have measured and characterized. They have shorelines that Cassini mapped in detail across multiple flybys, some smooth and gradual like tidal flats, others sharp and steep like the rocky coasts of volcanic islands. They have tides, small ones, driven by Saturn's gravitational pull as Titan orbits in a slightly eccentric path, amounting to perhaps half a meter of rise and fall over Titan's 16 Earth-day orbital period. They have waves. Cassini detected transient bright features on the surface of several seas during later flybys, nicknamed Magic Islands, which scientists now believe may be vast patches of nitrogen bubbles fizzing rapidly out of the liquid triggered by seasonal temperature changes or by the mixing of methane-rich and ethane-rich fluid layers, or possibly small wind-driven capillary ripples catching the radar beam at just the right angle. These seas even appear to have something resembling wetlands surrounding them. Analysis of Cassini thermal data suggested that the terrain around Ligia Mare may be saturated with liquid hydrocarbons, creating marshy borderlands not unlike the boggy shores around terrestrial lakes in tundra regions. Modelling studies predict that cyclonic storms could form over the northern seas during Titan's summer, driven by intense evaporation from the warming liquid surface storms that might produce gale-force winds exceeding 70 km per hour and torrential methane rainfall. Weather on Titan is not a metaphor. It is real meteorology, governed by the same fluid dynamics and thermodynamics that drive hurricanes and monsoons on Earth. And it is weather made entirely of substances that would kill you. The rain deserves careful attention because rain is one of the most psychologically normalizing phenomena in human experience. Rain means growth, renewal, the familiar smell of wet earth. It is the sound you fall asleep to. It is comfort. On Titan, rain is liquid methane falling from methane clouds at a terminal velocity slower than rain on Earth, because the atmosphere is thicker and the gravity is much weaker, roughly 1/7 of what you feel on Earth's surface. Titan's raindrops would be significantly larger than terrestrial raindrops, perhaps as large as a centimetre across, and they would drift down through the dense nitrogen air almost lazily. The experience might seem gentle, even peaceful, but each of those drops is a bead of cryogenic hydrocarbon at -179 degrees Celsius. Contact with exposed skin would produce instant cryogenic burns, comparable to liquid nitrogen exposure. The drops would condense and frost over any surface not actively heated. You could stand in a rain that looks like rain, sounds like rain, and falls like rain and be killed by it. The rivers this rain feeds are equally deceptive. Cassini's radar mapped extensive branching channel networks across Titan's mid-latitude and equatorial regions. Some are wide, braided systems resembling the outwash plains of glacial rivers. Others are narrow, deeply incised canyons. One channel system near the North Polar region was measured at roughly half a kilometre wide and more than 500 metres deep, a methane river gorge, comparable in scale to some of the more dramatic canyons carved by water into Earth's surface. These channels carry liquid methane and dissolved nitrogen from highlands down toward the polar seas, eroding the water ice bedrock along the way and depositing hydrocarbon sediment in deltas and floodplains. The erosion processes dissolution, abrasion, freeze-thaw cycling mirror those on Earth. The chemistry performing them is completely alien. Then there are the dunes. Covering roughly 13% of Titan's total surface area, primarily in a broad band stretching around the equator between roughly 30 degrees north and 30 degrees south latitude, vast fields of linear dunes extend for hundreds of kilometers in parallel rows that can be individually traced across entire radar swaths. On Earth, dunes are made of silicate sand, tiny grains of quartz and feldspar worn from mountains by wind and water over millions of years. On Titan, the dune material is organic. It is composed of the same tholin particles and other complex hydrocarbon grains that drift down from the upper atmosphere, accumulated over immense spans of time and sculpted by Titan's low-altitude winds into long, regular ridges up to 100 meters tall. From orbit, these dune fields look strikingly like the sand seas of the Sahara or the Great Ergs of Namibia. The patterns are so geometrically similar that planetary scientists use the identical terminology longitudinal dunes, Barchan forms, star dunes to classify them. But the sand is not mineral. It is frozen organic chemistry shaped by a nitrogen wind under an orange sky. Stand back from all of this and take in the complete picture. Titan has a thick nitrogen atmosphere with active weather. It has clouds that form, drift, and produce precipitation. It has rain that falls to the surface, collects into rivulets and rivers, and flows downhill through carved channels towards standing bodies of liquid. It has lakes and seas with measured shorelines, depths, compositions, and tides. It has dune fields shaped by prevailing winds. It has seasonal variation driven by Saturn's roughly 29.5-year orbital period around the Sun. Its atmospheric circulation includes superrotation in the upper layers and equator-to-pole transport of methane vapor. It has a surface pressure comfortable enough that a human body could survive without mechanical pressurization. No other world anywhere in the solar system offers this combination of features, not one. Mars has a thin atmosphere and ancient dry river valleys etched into its surface, but no standing liquid today, no active rain, no functioning surface weather cycle involving liquids flowing across the ground. Venus has a crushing, scorching atmosphere with extreme meteorological violence, but its surface is a kiln at more than 460 degrees Celsius where lead would melt in minutes. Europa and Enceladus harbour liquid water, but beneath kilometres of ice, with no atmosphere you could stand in and no visible surface hydrology. Only Titan presents a complete, functioning surface environment with clouds, rain, rivers, lakes, seas, dunes, wind, and seasons, a world that operates the way Earth does in its broadest mechanical strokes. And every single component of that environment is built from chemistry that would destroy a human being. The atmosphere provides pressure, but not oxygen. The rain is cryogenic fuel. The rivers carry hydrocarbons at temperatures that would freeze shatter exposed bone. The lakes and seas are pools of liquefied natural gas you could not float in, could not swim through, and could not survive falling into for more than a few seconds. The bedrock is water ice performing the role of stone. The sand is organic soot. The temperature makes a mockery of every insulation system humans have ever built for terrestrial use. The light is so faint that noon resembles late dusk, and the entire world sits so far from Earth that a distress call, even travelling at the ultimate speed limit of the universe, they would take more than 70 minutes to arrive, and another 70 for any reply to come back, assuming anyone on Earth could help at all. This is not a world that announces its hostility with obvious barrenness or alien strangeness. This is a world that dresses its hostility in the most familiar clothing the solar system has to offer. Every geographic feature you learn to name as a child, every process you associate with a living, breathing planet, exists on Titan, in a form that has been quietly redefined into something lethal. When Cassini finally dropped below the horizon, the link was lost forever. No second chance, no reboot, no follow-up surface mission for at least another decade. But in that narrow window of contact, the probe had measured everything its instruments could reach: temperature, atmospheric composition at multiple altitudes, wind speed and direction during descent, light levels at the surface, the mechanical properties of the ground upon impact, the methane humidity of the near-surface air, and the acoustic environment of an alien world. It photographed a landscape that looked like a cold, wet riverbed after a flood pebbles. Dark sediment, distant elevated terrain, all of it wrapped in that dim amber light. It recorded the sound of alien wind through a microphone never designed to hear anything so strange. And it sent all of that data on a journey lasting more than 67 minutes at the speed of light, across more than 1.2 billion kilometers of empty space, back to a species that had never before landed, a working instrument on the surface of any world in the outer solar system. What Huygens found was not a dead, cratered ice ball. It found a world in motion, a world with active weather and a surface shaped by flowing liquid and wind erosion and atmospheric deposition. A world where the ground is frozen water and the rain is liquid fuel, and the air is thick and the light is dim, and nothing, absolutely nothing works the way your instincts expect it to. That is the world we are going to try to survive on. And the next stage of this story is about what that survival would actually demand, what you would need every hour of every day just to keep a human body alive in a place where Earth-like appearances mask a chemistry quietly engineered to destroy you. The convenient pressure, the thick air, the weather that looks so reassuringly familiar, all of it is a trap. And understanding exactly how that trap works requires going below the surface of the illusion into the brutal mechanics of cold, oxygen, power, water, and isolation that would define every waking moment of a life on Titan. Everything about Titan's surface looks like it should be survivable. The pressure feels right. The sky has clouds. The ground has texture and features your brain can pass. And none of that matters, because the moment you step outside without the right protection, Titan begins killing you in at least 4 different ways simultaneously. Not dramatically, not with explosions or visible danger, quietly, efficiently, through chemistry, thermodynamics, and distance. Start with the most immediate threat, the cold. Not cold the way a winter night is cold, or the way a walk-in freezer is cold, or even the way the South Pole in July is cold. Cold in a category that has no equivalent in the entire history of human habitation or exploration on Earth. At -179 degrees Celsius, exposed human skin does not simply get frostbitten, it flash freezes. The water in your cells crystallizes so rapidly that the tissue becomes rigid before pain signals can fully propagate. In laboratory tests, biological tissue exposed to liquid nitrogen, which boils at -196 degrees Celsius, only 17 degrees colder than Titan's surface, becomes brittle enough to shatter within seconds. Your fingers would not go numb on Titan. They would become solid. Your eyes would freeze open. The moisture on your lips, in your nostrils, on the surface of your corneas, would crystallize into a thin shell of ice before you could blink. An unprotected human being on Titan's surface would lose consciousness within roughly 15 seconds from nitrogen asphyxiation, the same time frame as in any oxygen-free atmosphere, but the cold would be destroying. Exposed tissue simultaneously, flash freezing skin and extremities, even as the brain shut down from oxygen starvation. The two processes would race each other, and both would win. And here is the part that makes Titan's cold uniquely dangerous compared to, say, the vacuum of space. In vacuum, heat loss is surprisingly slow. Space is cold in the theoretical sense. The cosmic background temperature is just a few degrees above absolute zero, but there is nothing to conduct or convect heat away from your body except radiation, which is a gradual process. Astronauts performing spacewalks outside the International Space Station actually struggle more with overheating than freezing, because their bodies generate metabolic heat faster than radiation can remove it into the void. Spacesuits on the International Space Station carry cooling systems, not heaters, because the insulating vacuum keeps body heat trapped inside the suit. But on Titan, the situation reverses completely. You are not in vacuum. You are immersed in a thick, dense atmosphere, 1.5 times the pressure of Earth's air, composed almost entirely of molecular nitrogen at -179 degrees. That gas is in direct physical contact with every square centimetre of whatever you are wearing. Convection, the process by which moving fluid carries heat away from a warm object, becomes ferociously efficient in a dense, cold atmosphere. The nitrogen molecules collide with your suit surface billions of times per second, each collision carrying away a tiny fraction of thermal energy. Titan's air would strip heat from an uninsulated suit or habitat wall, the way a fast-flowing river strips warmth from a swimmer relentlessly, on every surface, all at once. The thickness of the atmosphere that makes pressure so conveniently Earth-like also makes the cold transfer rate terrifyingly fast. The very feature that seems like Titan's greatest gift, its human-compatible air pressure, becomes the engine that accelerates lethal heat loss beyond anything a human has ever faced in any natural environment. This means that every structure, every vehicle, every suit, and every piece of equipment that touches the outside environment on Titan must be wrapped in insulation far more aggressive than anything used in polar exploration or even in current spacesuit design. NASA's Dragonfly rotorcraft, currently being assembled for its 2028 launch, will be encased in a 3-inch thick layer of specialized foam insulation rated for temperatures below -185 degrees Celsius. Engineers at the Johns Hopkins Applied Physics Laboratory have been testing this foam in a dedicated titangent environment chamber, a sealed room chilled to Titan's surface temperature and filled with nitrogen gas at 1 Na, half bars of pressure to verify that the insulation maintains structural integrity and thermal performance over long durations. Even a small crack, a tiny breach where the cold nitrogen air could reach the warm interior, would create a thermal short circuit that could drain a system's heat budget in hours. For a human habitat, the insulation challenge is orders of magnitude worse. A crude structure on Titan would need to maintain an interior temperature of roughly 20 degrees Celsius, a difference of nearly 200 degrees from the outside air. Maintaining that gradient continuously in a dense convective atmosphere requires enormous and uninterrupted power. Every watt of heat that leaks through the walls must be replaced. Every door that opens, every airlock that cycles, every seal that degrades even slightly becomes a pathway for lethal cold to enter the living space. There is no margin for power failure. On Mars, if your heating system fails, you have hours or perhaps days before the thin atmosphere and lower temperature differential make conditions fatal. On Titan, the thermal mass of the surrounding dense nitrogen atmosphere would begin cooling an unheated habitat within minutes. The walls would frost over on the inside, condensation would freeze, any liquid water in the structure would begin solidifying. A human being inside a habitat that lost heating on Titan would be in mortal danger within an hour. Not days, not even a full work shift. An hour. Now add the oxygen problem. This is separate from the cold and equally absolute. Titan's atmosphere contains no free oxygen. It is not hiding in trace quantities. It is not locked in a form you could liberate with a simple chemical reaction at the surface. The atmosphere is nitrogen and methane, and the surface is water ice and hydrocarbon sediment. Oxygen atoms exist on Titan locked inside the water ice bedrock, bound in carbon dioxide ice that may exist in small deposits, possibly dissolved in trace amounts in the subsurface. But there is no atmospheric oxygen for a human being to breathe, and there is no natural process on the surface producing it. Every molecule of oxygen a human needs on Titan must be either brought from Earth, manufactured on site, or extracted from local materials using energy-intensive processes. The most plausible source of oxygen on Titan is the water ice itself. The surface and subsurface are made of it. In principle, electrolysis splitting water molecules into hydrogen and oxygen using electricity could provide breathable oxygen from local ice. But the ice on Titan is not sitting in convenient chunks you can scoop into a melting pot. It is bedrock. It is the structural foundation of the landscape, frozen at -179 degrees Celsius to a rigidity that makes conventional extraction tools useless. Mining water on Titan means quarrying ice that resists cutting and drilling, transporting it to a heated facility, melting it, which requires enormous energy input given how cold it is, and then electrolyzing the resulting water. Every step in that chain demands power. Every step depends on machines functioning reliably in an environment where most lubricants would freeze solid, most seals would become brittle, and most mechanical components would experience thermal contraction far beyond their design tolerances, unless specifically engineered for cryogenic conditions. And you need a lot of oxygen. A single human being at rest consumes roughly 400 litres of oxygen per day. Under the moderate physical activity of surface operations, that number can double. A small crew of 6 people working on Titan's surface would consume thousands of litres of oxygen daily, all of it manufactured from ice that must be mined, melted, and processed. The energy required for this alone, not heating, not lighting, not communications, just breathing, would be substantial. A single radioisotope thermoelectric generator of the type Dragonfly will carry produces roughly 110 watts of electrical power. That is enough to charge a battery for a robotic drone. It is not remotely enough to support a human crew's oxygen production, heating, water processing, and life support. A crude settlement on Titan would need multiple kilowatts of continuous power, likely tens of kilowatts, which means either a small nuclear fission reactor or a bank of advanced RTGs far more powerful than anything currently deployed in space exploration. The power problem on Titan is not an inconvenience. It is the central engineering constraint around which every other system must be designed. Heat and oxygen are the 2 things that will kill you fastest on Titan. But surviving beyond the first day requires solving a longer list of problems, each one compounded by the distance from Earth and the alien chemistry of the environment. Water is essential for human survival, and Titan has an almost unlimited supply of it in the worst possible form. The surface is made of water ice. The bedrock beneath the hydrocarbon sediment is water ice. The pebbles Huygens photographed were water ice. In terms of raw volume, Titan has more accessible water than almost any other solid body in the solar system, but that water is frozen at a temperature where it is functionally indistinguishable from stone. You cannot chip it away with a hand tool any more easily than you could chip granite with a pocket knife. You need powered mining equipment, drills, cutters, or thermal lances to extract it. Then you need to transport the ice to a heated facility, melt it using energy that must come from your nuclear power supply, purify it to remove any dissolved hydrocarbons or organic contaminants from the tholin-coated surface layer, and only then do you have drinkable water. The contamination issue is real and important. Titan's surface is coated in a thin but persistent layer of organic chemistry. Tholins, polycyclic aromatic hydrocarbons, nitrile compounds, and other complex molecules settle out of the atmosphere continuously and accumulate on every exposed surface, including the ice. Any water extracted from surface ice would need to be tested and filtered for these contaminants, some of which, like hydrogen cyanide, which has been detected in Titan's atmosphere, are actively toxic to humans. You are not simply scooping clean snow into a pot. You are mining contaminated ice from a cryogenic surface, in an environment where your mining equipment must operate at temperatures that would freeze most hydraulic fluids solid and crack most standard steel alloys. Food production on Titan presents an entirely different category of challenge. Growing plants requires light, warmth, water, carbon dioxide, and soil nutrients. Titan has almost none of these in usable form at the surface. The light is far too weak for photosynthesis. Even the hardiest low-light crop plants require hundreds of times more photon flux than Titan's surface receives. The temperature is lethal to any known organism and would freeze soil biology solid in microseconds. The atmosphere contains no carbon dioxide in meaningful quantities. It is nitrogen and methane. The water is frozen stone. The soil is organic soot, not mineral earth with microbial communities. Any agriculture would have to occur inside fully enclosed, artificially lit, heated, pressurized greenhouses, with manufactured atmospheres containing the right balance of oxygen, carbon dioxide, nitrogen, and humidity. Every calorie of food produced on Titan would cost more energy than the calorie itself contains, because the energy required to maintain growing conditions in an environment that hostile heating alone would dominate the budget far exceeds the metabolic energy stored in the resulting crops. For any early Titan settlement, food would almost certainly need to be shipped from Earth, a supply line stretching more than 1 billion kilometers, with transit times measured in 6 to 7 years using current propulsion technology. A crew that runs low on food cannot order a resupply and receive it next week, or next month, or even next year. They would wait the better part of a decade. Every meal on Titan would be a reminder of how far away the nearest farm is. Any crewed mission would need to launch cargo vessels carrying years of food supplies long before the crew themselves departed, pre-positioning everything at Titan and confirming its arrival before a single human being committed to the journey. Now, consider movement. Getting around on Titan's surface is paradoxically both easier and harder than you might expect. The low gravity, roughly 1/7 of Earth's, means you weigh about 1/7 of what you weigh at home. A person who weighs 80 kilograms on Earth would weigh about 11.5 kilograms on Titan. In principle, you could carry heavy equipment with less effort, jump higher, and move with less muscular strain. But you would not be moving in a light spacesuit. You would be encased in a heavily insulated, multi-layered thermal protection suit with its own heating system, oxygen supply, carbon dioxide scrubbing, communications equipment, battery packs, and emergency reserves. This suit would be bulky, rigid in places where insulation is thickest, and heavy even in Titan's reduced gravity. Walking across a surface made of water ice and hydrocarbon sand, potentially coated in a slippery layer of frozen organic residue, wearing a suit designed primarily to keep you from freezing to death, the experience would be closer to wading through a construction site in a bomb disposal suit than to the graceful bounding you see in Apollo footage from the Bode Moon. The thick atmosphere and low gravity do offer one extraordinary advantage, however, and it is the one genuinely favourable factor on Titan that has no equivalent on any other world: flight. Titan's nitrogen atmosphere is about 4.5 times denser than Earth's air at sea level, and the surface gravity is roughly 7 times weaker than Earth's. The combination of these two factors means that the energy required to generate aerodynamic lift on Titan is dramatically less than on Earth, roughly 38 times less, by some calculations. A human being wearing wings on Titan, actual physical rigid wings strapped to their arms and torso, could theoretically generate enough lift through sustained arm-powered flapping to achieve controlled, sustained flight above the surface. This is not speculation. The aerodynamics have been modelled and published in peer-reviewed papers. Of course, you would still need a heated suit and an oxygen supply, which would add mass and reduce the elegance of the concept. But the physics is real. Flight on Titan is easy in a way it is nowhere else in the solar system, and NASA's Dragonfly mission exploits exactly this advantage. An 8-rotor nuclear-powered drone that will hop between landing sites tens of kilometers apart, covering distances that would take a Mars rover months to traverse. For a human crew, flight-capable vehicles would be the primary mode of long-distance transportation. Wheeled rovers would face serious challenges on Titan's surface. The mix of water-ice terrain and loose organic sediment could create traction problems, and the extreme cold would make tire materials brittle and mechanical systems sluggish. But a small helicopter or VTOL aircraft, operating in that thick nitrogen atmosphere under that weak gravity, could carry significant payloads with relatively modest engine power. The irony is striking. You cannot walk comfortably on Titan. You cannot drive easily, but you could fly. The most psychologically crushing survival constraint, however, is not physical at all. It is distance. The distance between Earth and Saturn changes constantly as both planets move through their orbits. At its closest approach, Saturn is about 1.2 billion kilometers from Earth. At its farthest, roughly 1.7 billion kilometers. Most of the time, the distance falls somewhere in between. At those distances, a radio signal traveling at the speed of light takes between 67 and 95 minutes to make the one-way trip. A round-trip communication: you say something, the signal travels to Earth, someone responds, and their reply travels back, takes between 2 hours and 15 minutes and over 3 hours. Think about what this means in practical terms. If a crew member on Titan suffers a medical emergency, a suit breach, a broken bone, a chemical exposure from a tholin-contaminated ice sample, they cannot call for advice and receive an answer in real time. They radio Earth describing symptoms and requesting guidance. Then they wait. For more than an hour, their signal crawls across the solar system at 300,000 kilometers per second. It arrives at a deep space network antenna on Earth. The medical team listens, confers, formulates a response. They transmit the answer. It crawls back. By the time the crew on Titan hears the first word of guidance, the emergency has been ongoing for over 2 hours, at minimum. For acute crises, a habitat fire, an airlock failure, a suit heater malfunction in the open air, a sudden decompression event, 2 hours might as well be 2 days. The patient has either stabilized, improvised a solution, or died long before the reply arrives. The communication delay does not merely slow help, it eliminates it. This communication delay is fundamentally different from the delay experienced by Mars missions. Mars at its most distant is about 24 minutes away by light speed. That is frustrating but manageable for many scenarios. Titan is roughly 4 times farther. The delay is long enough that real-time troubleshooting is impossible. Every crew member on Titan would need to be trained as a generalist, capable of performing emergency medicine, mechanical repair, electrical diagnostics, chemical hazard response, and psychological crisis management without consulting Earth. The station would need comprehensive onboard reference systems, artificial intelligence diagnostic tools, and enough spare parts and redundant systems to handle any foreseeable failure internally. There would be no phoning home, not in any meaningful, timely sense. The psychological weight of that isolation is difficult to overstate. Human beings are social animals who have never in their evolutionary history been more than a few days' travel from other humans. Even the most remote Antarctic research stations can reach the outside world by satellite phone, with a delay measured in seconds. Submarine crews operate in communication silence for weeks, but know they can surface and reach help within hours if necessary. A crew on Titan would be the most isolated group of human beings who have ever lived. Their nearest help would be not just far away, but fundamentally unreachable in real time. If something goes catastrophically wrong, a structural failure, a disease outbreak, a critical system loss, they cannot be rescued. No ship can reach Titan in less than several years with current technology. There is no cavalry, there is no evacuation. There is only the equipment they brought, the training they received, and the decisions they make in the moment. Every hour of every day on Titan, a human crew would be engaged in an unrelenting war of maintenance, not against dramatic threats, meteorite impacts, or alien organisms or equipment explosions, but against the slow, persistent erosion of systems by cold, chemical contamination, and mechanical degradation. Seals degrade in cryogenic environments. Lubricants thicken. Metal contracts and expands across thermal gradients that stress joints and welds. The tholin particles settling constantly from the atmosphere would coat every exterior surface. Optics, solar sensors, antenna dishes, mechanical joints, suit visors with a thin, sticky, organic film that would need to be regularly cleaned. Any surface exposed to the air and not actively maintained would gradually become coated, fouled, and eventually compromised. Maintenance on Titan would not be a scheduled task performed between more interesting activities. It would be the primary activity. Survival depends on systems. Systems depend on maintenance. Maintenance depends on tools, parts, training, and energy, all of which must function in an environment that actively degrades every material and mechanism you rely on. Consider what a single EVA, an extravehicular activity, a trip outside the habitat would involve. You do not simply put on a suit and walk out the door. You enter an airlock that must be carefully temperature managed to avoid thermal shock to your equipment. The airlock cycles, replacing the warm, oxygenated interior air with cold, nitrogen-methane atmosphere, while gradually lowering the temperature of your suit's exterior layers to avoid catastrophic condensation and icing. When you open the outer door, this process takes time, potentially 30 minutes or more. Once outside, your suit's heating system must maintain your body temperature against the dense, frigid atmosphere constantly pulling heat away from you. Your oxygen supply is finite. carried in tanks on your back or generated by a small chemical system. Your visibility is limited by the dim light and the orange haze. Your communications with the habitat, a local suit-to-habitat radio, works fine over short distances, but any message to Earth disappears into that 70 to 90-minute void. Your mobility is constrained by the bulk of your insulation layers, and every minute you spend outside is a minute on a countdown. Oxygen remaining, battery charge remaining, heating fuel remaining. There is no lingering. There is no casual observation. Every EVA is a tightly planned, time-limited operation with hard abort criteria. You go out, perform your task, and return before your consumables run low. If something goes wrong outside, a suit heater fails, a seal cracks, a helmet fogs from thermal differential, you have minutes, not hours, to get back inside. And through all of this, the landscape around you looks almost normal. The sky has clouds, the ground has texture. There might be a faint pattering of methane rain against your visor. In the distance, a dark line of liquid might mark the edge of a hydrocarbon lake. The dunes roll away to the horizon like desert sand. If you squint, if you let your instincts take over, it almost looks like a cold, overcast day on a strange beach on Earth. Your brain wants to relax. Your training tells you not to, because the clouds are methane, the rain is liquid fuel, the lake is cryogenic poison, the sand is organic soot, the ground is frozen water, the air is unbreathable, and you are standing inside a machine that is the only thing keeping you alive. Every element of survival on Titan reduces to the same core equation. Energy in must exceed energy out, or you die. Heat escapes through your insulation, you must replace it. Oxygen is consumed by your lungs, you must manufacture more. Water is locked in ice, you must melt it. Food cannot grow, you must ship it, or find a way to synthesize it. Equipment degrades, you must repair it. Communication is delayed, you must solve problems alone. And all of this must happen continuously, without interruption, for as long as anyone remains on that surface. The engineering is not theoretically impossible. Nuclear fission reactors can provide tens of kilowatts. Cryogenic insulation materials exist and are improving. Electrolysis systems for oxygen production are well understood. Robotic systems can perform exterior maintenance in environments too hostile for frequent human EVs. The individual components of a Titan survival system all exist in prototype or proven form. The challenge is that every single one of them must work, all the time, simultaneously, in an environment where failure of any one system cascades into failure of the others. Heating failure leads to oxygen system freeze. Oxygen failure leads to crew incapacitation. Communication failure leads to unanswerable emergencies. Power failure leads to everything. On Mars, a suited astronaut who encounters a problem can often improvise. The thin atmosphere and moderate cold Mars averages about -60 degrees Celsius. Severe by Earth standards, but more than 100 degrees warmer than Titan, give you time to think, assess, and react. You can walk back to your habitat at a reasonable pace. You can patch a suit leak with emergency tape and still have minutes of pressure margin because the outside pressure is so low. The communication delay with Earth is long enough to be frustrating, but short enough to get guidance within a roughly 40-minute round trip. Mars is hostile, but it is hostile in a way that gives you room to make mistakes and recover from them. Titan does not offer that room. The thermal environment is so extreme, the chemistry so alien, and the distance from help so vast that the margin between survival and death is measured in minutes and millimeters of insulation. Everything must work. Everything must be maintained. Everything depends on power that cannot come from the sun, and every person standing on that surface must understand that they are not exploring a new world. They are operating a life support machine that happens to be parked on one. The systems that keep them alive are the mission. The science, the exploration, the discovery, all of that happens only after survival is guaranteed. And on Titan, survival is never guaranteed. It is earned, hour by hour, watt by watt, breath by breath, in a place that wraps its danger in the most familiar-looking scenery the solar system has to offer. But survival is only half the problem. The other half is the surface itself, the methane seas, the organic dunes, the haze-coated ice plains, and the chemistry that makes Titan one of the most scientifically fascinating and operationally treacherous places any human crew could ever attempt to work on. Now imagine the suit is on, the airlock has cycled, and you are standing outside. The heating system hums against your ribs. The oxygen gauge reads full. The visor is clear, for now, and the light filtering through Titan's permanent haze casts everything in shades of dull amber and brown. You look around, and what you see is a world that has been studied by radar, by spectroscopy, by atmospheric probes, and by decades of computational modelling, but that no human eye has ever directly witnessed. Everything we know about this surface comes from instruments. What those instruments have revealed is a landscape that operates by rules familiar enough to recognise and alien enough to be genuinely dangerous to anyone who assumes the resemblance means safety. Start with the seas, because the seas are where the deception runs deepest. Cassini's radar mapped 3 major hydrocarbon seas in Titan's northern polar region, along with dozens of smaller lakes scattered across the high latitudes. These are not abstract features on a chart. They are bodies of liquid with measured depths, characterized compositions, observed seasonal changes, and modeled current systems. Kraken Mare alone covers an area of roughly 400,000 square kilometers, comparable in extent to the Black Sea on Earth. Its composition is a mixture of methane, ethane, and dissolved nitrogen, with the ratio varying by location and depth. In some areas, the liquid is predominantly methane. In others, ethane dominates. The difference matters because methane and ethane have different densities, different viscosities, different evaporation rates, and different behaviors when nitrogen comes out of solution. A methane-rich region of Kraken Mare behaves differently from an ethane-rich region, in the same way that a freshwater lake behaves differently from a saltwater bay, similar in appearance, different in chemistry, and different in what happens to anything you put into it. The depth of these seas is not trivial. Radar altimetry from Cassini measured Lichgia Mare at roughly 200 meters deep in its central basin. Kraken Mare is believed to be deeper still in places, though precise depth measurements were harder to obtain because its composition, particularly the higher ethane fraction in some regions, absorbs radar energy more effectively, making the bottom harder to detect. These are not shallow puddles. They are deep, cold, chemically complex reservoirs of liquid hydrocarbon sitting under a dim orange sky. What would it actually mean to operate near one of these seas? The question is not academic. Future mission concepts have proposed sending submersible probes into Kraken Mare, and any long-term human presence on Titan would almost certainly need to access the polar regions where the largest concentrations of surface liquid exist, both for scientific study and because the seas represent the densest reservoir of accessible hydrocarbons on the Moon, which could theoretically be processed into fuel or chemical feedstocks. First, the liquid itself is cryogenic. At -179 degrees, any equipment that contacts the surface of a methane sea must be rated for temperatures that would make most standard engineering materials catastrophically brittle. Metals contract unevenly at cryogenic temperatures, creating stress at joints and welds. Polymers crack, lose elasticity, and shatter under loads they would easily bear at room temperature. Seals designed for merely cold environments, even those rated for Antarctic conditions or low Earth orbit thermal cycling, would fail within minutes of immersion in liquid methane. Any vessel designed to float on or travel through a Titan sea would need to be built from specialized cryogenic-grade alloys, composites tested in liquid nitrogen baths, and gaskets made from materials that remain flexible below -190 degrees, and it would need to float, which is not guaranteed. Liquid methane has a density of roughly 450 kilograms per cubic meter, significantly less dense than water, roughly 1,000 kilograms per cubic meter. A vessel that floats comfortably on a terrestrial ocean would ride dangerously low or sink outright in a methane sea, unless its hull volume and displacement are specifically engineered for the lower density liquid. Every principle of naval architecture that humans have developed over thousands of years of ocean engineering would need to be recalculated for a fluid that weighs less than half as much per unit volume as seawater. Second, the seas are not chemically inert. Nitrogen dissolved in the liquid methane can come out of solution when conditions change, when the liquid warms slightly during seasonal transitions, or when methane-rich and ethane-rich currents mix. Laboratory experiments and modelling studies have shown that this degassing can produce vigorous effervescence, sudden, widespread bubbling events that could destabilise the surface of the liquid and create hazardous conditions for anything floating on it. The magic islands detected by Cassini on multiple seas may be exactly this phenomenon, nitrogen fizzing out of solution across vast areas of the surface. A vessel caught in one of these degassing events would experience rapidly changing buoyancy as the liquid beneath it became aerated with gas bubbles, reducing its effective density and potentially causing the vessel to sink lower or lose stability. This is not a theoretical concern. It is a modelled, physically grounded hazard that any Titan sea surface mission would need to account for. Third, the shorelines of these seas are not simple beaches. Cassini's radar revealed complex terrain surrounding the major seas, including what appear to be flooded lowlands, marshy zones saturated with liquid hydrocarbons, and steep-sided basins with sharp rims that suggest dissolution or collapse of the underlying water ice bedrock. Some of these features resemble terrestrial karst topography, the sinkholes, caves, and collapsed terrain you find in limestone regions on Earth where groundwater has dissolved the rock from beneath. On Titan, the dissolving agent is not water. It is liquid methane and ethane, eating into the water ice bedrock over geological time. Walking near a Titan shoreline would mean navigating terrain that might be undermined, unstable, or saturated with liquid hydrocarbons just below the surface. A step onto what looks like solid ground could break through a thin crust into a subsurface pocket of liquid methane. In a heated suit with limited mobility, that kind of fall could be catastrophic. Now move inland, away from the seas, into the equatorial regions where the landscape changes character entirely. Here, the vast dune fields dominate. Hundreds of kilometers of parallel organic ridges stretching to the horizon, shaped by winds that blow primarily from the west. Despite Titan's eastward rotation, a pattern that puzzled scientists for years because it seems to contradict the expected wind direction. The current explanation involves the interaction between Titan's tidal forces from Saturn and its atmospheric circulation, producing occasional bursts of strong eastward wind during equinox periods that dominate the long-term dune-shaping process despite the prevailing westward flow. The result is a dune landscape that looks superficially like a terrestrial sand sea, but was sculpted by a fundamentally different wind regime, driven partly by gravitational interactions with a gas giant. The dune material itself poses operational challenges that go beyond its exotic composition. Tholin particles are sticky. They are electrostatically active in Titan's atmosphere, carrying charges that cause them to cling to surfaces, clump together, and resist being brushed away. On the Moon, Apollo astronauts discovered that lunar dust, electrostatically charged silicate particles, invaded every seal, joint, and mechanism on their suits and equipment, degrading performance and damaging surfaces. Titan's organic particulates would present a similar but chemically distinct problem. The material is not just physically abrasive, it is composed of complex organic molecules, including nitrogen-bearing compounds like nitriles, some of which hydrogen cyanide, for instance, are toxic. A suit or vehicle operating in the dune regions would accumulate a coating of this material on every exterior surface. Visor clarity would degrade. Optical instruments would lose sensitivity. Mechanical joints would accumulate residue that could impede motion. And when equipment returned to a heated airlock, the warming of this accumulated Tholin material could release volatile organic compounds into the interior atmosphere, creating a chemical contamination risk that would need to be managed with careful decontamination protocols before any suit or tool entered the habitable space. This is not a minor operational nuisance. It is a persistent, mission-defining maintenance burden. Every sortie onto Titan's surface would return coated in material that is both physically intrusive and chemically hazardous. Cleaning protocols, filtration systems, and air quality monitoring would be constant requirements. The organic chemistry that makes Titan scientifically fascinating, the same chemistry that draws astrobiologists and prebiotic researchers to this moon above almost any other destination, would also be the chemistry that, slowly, persistently fouls every piece of equipment that touches the surface. And it is that chemistry that makes recent scientific developments about Titan so significant. In 2025, Two major findings reshaped the scientific picture of this world in ways that any future human mission would need to account for. The first was a study published in the journal Nature in December of 2025. For more than a decade, planetary scientists had accepted, based on Cassini gravity measurements and models of Titan's interior, that the Moon harbored a global subsurface ocean of liquid water beneath its ice crust. The evidence came from the way Titan's shape deformed slightly as Saturn's gravity pulled on it during its orbit. This tidal flexing was larger than expected for a completely solid body, suggesting that a liquid layer existed somewhere between the surface ice and the rocky core, decoupling the crust from the deep interior and allowing it to flex more freely. The subsurface ocean became one of Titan's most celebrated features, a hidden reservoir of liquid water that, combined with the organic-rich surface chemistry, made the Moon a top-tier target for astrobiology. The December 2025 study overturned that consensus. A team led by researchers at NASA's Jet Propulsion Laboratory reanalyzed the Cassini radiometric tracking data using improved signal processing techniques. What they found was a strong signature of tidal dissipation energy being lost to internal friction as Titan flexes that was inconsistent with the presence of a global liquid water layer. The physics is counterintuitive but clear. A liquid ocean beneath the ice crust would actually reduce the amount of tidal energy dissipated in the layers below it, because the liquid decouples the crust from the deeper interior. The observed dissipation was too high for an ocean to be present. Instead, the data were best explained by a model in which the dissipation is concentrated in a high-pressure ice layer deep in the interior, near its melting point warm enough to be soft and slushy, but not fully liquid. This does not mean water is entirely absent from Titan's interior. The study's authors were careful to note that localized pockets of liquid water could still exist within the slushy ice layer, sustained by local heat sources, tidal flexing, or chemical interactions with ammonia that lower the melting point of ice. The Moon probably hosts liquid water in isolated reservoirs, pockets trapped in the deep ice where local conditions allow melting to occur. But the picture of a vast, continuous, globe-encircling ocean, hundreds of kilometers beneath the surface, the underground sea that made Titan seem like a cold, distant cousin of Europa or Enceladus, another member of the growing club of ocean worlds, now appears to be wrong. Or, at the very least, not supported by the best available data. This matters enormously for habitability assessments and for future mission planning. A global subsurface ocean would have been a potential habitat for microbial life, a target for future deep drilling missions, and a water resource accessible in theory to any long-term human presence. Localized water pockets are far harder to find, far harder to access, and far less useful as a resource. The Dragonfly mission, which will carry geophysical instruments capable of measuring Titan's tidal response and detecting seismic activity from the surface, will provide a critical further test of whether any substantial subsurface liquid exists, and in what form and at what depth. But for now, the scientific consensus has shifted. Titan's interior is probably not the ocean world we thought it was for the last 15 years. It is something more ambiguous. A world with water locked in a partially molten, high-pressure ice matrix, potentially harboring habitable niches in isolated pockets, but not in the sweeping, continuous, globally connected way a true subsurface ocean would imply. The second major finding came earlier in 2025, when NASA researchers published a study in the International Journal of Astrobiology outlining a mechanism by which cell-like structures called vesicles could theoretically form in Titan's hydrocarbon lakes. On Earth, vesicles are tiny spherical membranes made of amphiphilic molecules with one end that attracts water and another that repels it. When these molecules encounter water, they spontaneously assemble into hollow spheres, creating enclosed compartments that can trap other molecules inside. These compartments are considered a critical precursor to the first living cells. Life as we know it required some mechanism for separating inside chemistry from outside chemistry, and vesicles are the leading candidate for how that separation first occurred. The 2025 study proposed that a similar process could occur on Titan, but with the chemistry inverted. Instead of water-based amphiphiles forming vesicles in a water solvent, nitrogen-bearing organic molecules produced in Titan's atmosphere, nitriles and other compounds could act as amphiphiles in a methane-ethane solvent. The proposed mechanism involves these molecules washing down from the atmosphere during methane rain, accumulating on the surfaces of lakes, and self-assembling into thin films. When splashing or wave action creates droplets coated in these films, the result is enclosed vesicles, tiny compartments floating in the hydrocarbon liquid, each one a potential site for further chemical complexity to develop. This is not a claim that life exists on Titan. The researchers were explicit about that. What it is, however, is a demonstration that one of the critical steps in the origin of life, the formation of compartmentalized structures, could plausibly occur in a solvent system completely unlike water, at temperatures completely unlike Earth's, using chemistry completely unlike biology as we know it. If vesicles do form in Titan's lakes, they would represent an increase in molecular order and complexity in an extraterrestrial environment, a step on the road toward organization that, on Earth, eventually led to living cells. Whether that road leads anywhere on Titan is unknown, but the fact that the first steps are chemically plausible is remarkable. This is the context in which the Dragonfly mission becomes not just scientifically interesting, but operationally essential as a precursor to any human activity on Titan. Dragonfly is a car-sized, nuclear-powered, 8-rotor helicopter designed to fly through Titan's dense nitrogen atmosphere, land at multiple sites across the surface, and conduct detailed chemical analysis of the ground material at each location. It is the most ambitious surface mission ever designed for the outer solar system, and it will be the first aircraft to fly in the atmosphere of any world beyond Earth that is not Mars. Construction of the flight vehicle began in March of 2026 at the Johns Hopkins Applied Physics Laboratory in Laurel, Maryland. By April of that year, engineers had completed a fit check of the rotorcraft's top deck on the main body structure, the first time the physical shape of the lander came together in its flight configuration. The heat shield, built by Lockheed Martin, completed thermal structural testing in June of 2026, using concentrated solar energy at Sandia National Laboratory's Solar Tower facility in New Mexico, as Doppler, where hundreds of calibrated mirrors focused sunlight to temperatures of approximately 2,500 degrees Celsius on sections of the heat shield material, simulating the extreme conditions of atmospheric entry at Titan. The shield performed as designed even when engineers intentionally introduced defects to test failure modes. The mission passed its critical design review in April of 2025, clearing the way for full assembly and integration. It is scheduled to launch in July of 2028 on a SpaceX Falcon Heavy rocket from Kennedy Space Center in Florida, with arrival at Titan expected in 2034, after a cruise of approximately 6 years. Dragonfly will enter Titan's atmosphere encased in a protective aeroshell, deploy parachutes to slow its descent, then separate from the shell and fly under its own power to the surface. For its first landing, the initial landing site is near Titan's equator, in the region surrounding Selk crater, an impact structure roughly 90 kilometers in diameter. Scientists selected Selk because impacts on Titan's ice crust would have generated enormous amounts of transient liquid water from the melted ice, creating a temporary environment where liquid water mixed directly with the surface organic chemistry. That mixture, warm water interacting with tholin-rich organic material, would have created conditions remarkably similar to the prebiotic environments hypothesized for early Earth. If prebiotic chemistry advanced further at Selk than elsewhere on Titan, the molecular record of that advancement should still be preserved in the surface material, frozen in place when the meltwater refroze. Over a primary mission lasting more than 3 years, the rotorcraft will make flights of up to tens of kilometers at a time, hopping between sites and covering a total distance of roughly 115 kilometers from its initial landing location. At each site, it will use its onboard Dragonfly mass spectrometer DRAMs to analyze the chemical composition of surface materials, identifying organic molecules, their complexity, and their potential relevance to prebiotic chemistry. A suite of geophysical and meteorological sensors called DragMet will measure atmospheric conditions, seismic vibrations, and the electromagnetic environment at each landing site. The mission's flight plan is structured around Titan's day-night cycle. A single Titan solar day, called a T-Sol, lasts roughly 16 Earth days. During the long Titan night, Dragonfly will sit on the surface, recharging its battery from the MMRTG and collecting meteorological data. During the brief periods of flight, It will cover distances in under an hour that would take a wheeled rover months to traverse. The thick atmosphere and low gravity that make surface operations so difficult for humans make flight trivially easy for a well-designed rotorcraft. Dragonfly exploits the one genuine advantage Titan offers its flyable air to conduct a survey that would be impossible with any other type of surface vehicle. What Dragonfly finds at Selk Crater and the surrounding terrain will reshape our understanding of what Titan's surface chemistry actually is. Not what models predict, not what remote sensing suggests, but what is physically present in the ground when you analyze it molecule by molecule. If complex prebiotic molecules are abundant, if vesicle-forming amphiphiles are detected, if the chemistry shows signs of organization beyond simple photochemical products, then Titan becomes something more than a fascinating analog. It becomes evidence that the chemical foundations of life can arise in conditions radically different from Earth's. But none of that changes what it would mean to work there as a human being. The science is extraordinary. The operational reality is brutal. Every surface site Dragonfly visits is a place where a human crew would face the full weight of Titan's environmental hostility, the cryogenic temperatures, the unbreathable air, the sticky organic contamination, the weak light, the communication blackout, the constant need for power. A scientist standing where Dragonfly lands would see the same chemistry the rover analyzes, but through a visor fogged by thermal differential, in a suit that limits dexterity to the level of thick winter gloves, under time pressure set by oxygen reserves and battery life. Every sample collected would need to pass through a decontamination protocol before entering the habitat. Every tool used outside would need cleaning before being stored. Every excursion would be a calculated risk balanced against the scientific return. The terrain itself would add to the difficulty. Selk Crater's floor may be covered in a mix of water ice fragments from the original impact event, organic material accumulated from continuous atmospheric deposition over millions of years, and possibly refrozen cryolava from subsequent geological activity. This creates a surface with unknown and potentially highly variable mechanical properties. It could be firm, compacted, and traversable in some areas similar to the hard frozen ground Huygens encountered. It could be loose, granular, and treacherous in others, like walking on deep, unconsolidated sand. It could vary from one footstep to the next, with a firm crust covering softer material beneath, creating ankle-twisting hazards for anyone in a bulky thermal suit. Near the crater rim, the terrain could include steep slopes of shattered ice debris, loose organic sediment, and potentially unstable overhangs where erosion has undercut the surface. Without prior ground truth data, which Dragonfly will be the first mission to provide any human mission to Titan's surface, would be operating on terrain that has never been walked on, directly measured, or characterized by physical contact. Every step would be a small experiment in surface mechanics. Dragonfly is, in a very real and practical sense, the scout. It goes first. It tests the ground with its landing skids and its drill. It measures the chemistry with its mass spectrometer. It characterizes the terrain with its cameras and sensors. And only after its data are transmitted back to Earth, analyzed, debated, and incorporated into engineering models, can anyone begin designing a human mission with any confidence that the surface will support the weight, the anchoring forces, and the operational requirements of a crewed installation. There is also the question of what lies beneath the immediate surface layer, beyond just the revised subsurface ocean picture. Titan's ice crust is not necessarily static or geologically dead. There is evidence from Cassini that cryovolcanic features may exist on the surface regions where liquid water or water ammonia slurries from the interior have reached the surface through volcanic-like processes, erupting through the ice crust and spreading across the frozen landscape as cryolava before solidifying in the extreme cold. Several candidate cryovolcanic structures have been identified in Cassini radar images, though their interpretation remains debated among planetary geologists. If cryovolcanism is currently active or was recently active in geological terms, then Titan's surface is not just a frozen shell sitting passively over a cold interior. It is a dynamic boundary where interior fluids can breach the crust, altering the local chemistry dramatically and creating terrain features that could be structurally unstable, chemically reactive, or thermally anomalous compared to surrounding areas. A crew operating near a cryovolcanic feature would need to assess whether the ground beneath them is solid ice, frozen cryolava, or a thin cap over a subsurface fluid pocket, all without the luxury of geological surveys conducted in comfortable laboratory conditions. Even the atmosphere near the surface adds complexity that goes beyond its basic composition. Cassini and Huygens measurements showed that methane humidity at the surface varies by location and season. Near the polar seas, the air is closer to saturation. Methane fog could form at ground level under the right conditions, reducing visibility to meters and coating every surface in a thin film of condensed hydrocarbon. Near the equator, the air is drier, but the tholin haze still limits visibility and coats exposed surfaces. Wind speeds at the surface are generally low. Huygens measured roughly 1 meter per second near the ground during its descent, a gentle breeze by any terrestrial standard, but meteorological models predict that seasonal storms, particularly those associated with equinox transitions when Titan's atmospheric circulation pattern shifts, could produce gusts of 20 meters per second or more. 20 meters per second sounds modest compared to terrestrial hurricane winds, but in an atmosphere 4.5 times denser than Earth's, each cubic meter of moving air carries 4.5 times more mass, and therefore 4.5 times more kinetic energy. A habitat or vehicle caught in a Titan storm would experience wind loads comparable to a moderate gale on Earth, despite the nominally lower wind speeds, because the sheer density of the nitrogen atmosphere means each gust hits with substantially more force per unit area than the same wind speed would deliver in Earth's lighter air. All of this, the cryogenic seas, the sticky organic dunes, the undermined shorelines, the potential cryovolcanic hazards, the variable methane humidity, the persistent tholin contamination, the revised interior model, the tantalizing prebiotic chemistry converges on a single operational truth. Titan's surface is not a place where you can land, set up camp, and begin working with reasonable confidence that the environment will behave as expected. It is a place where every assumption must be tested, every surface must be characterized, every chemistry must be analyzed before you can trust it. The familiar appearance of clouds and rain and shorelines creates an instinct to treat the environment as manageable. The chemistry beneath that appearance demands the opposite. Dragonfly will be the first machine to systematically test those assumptions. What it discovers will determine whether a human presence on Titan is merely difficult or genuinely impossible with foreseeable technology. And that answer, whatever it turns out to be, will force a reckoning with the deepest question this world raises, not whether we can survive there, but what it means that a world this Earth-like in appearance is this far from Earth-like in reality. Every hostile world in the solar system announces itself. Mars greets you with a sky, the colour of rust, and an atmosphere so thin the horizon looks razor-sharp against black space at dusk. The moon offers nothing, no air, no colour, no sound, just a black sky and grey dust stretching to a sharp horizon. Venus hides its violence behind a veil of acid cloud, but the moment you descend through that veil, the truth is unmistakable. Nearly 500 degrees Celsius, 90 atmospheres of pressure, an atmosphere dense enough to crush a submarine. Europa's surface is a radiation-blasted sheet of ice scarred by fractures, the colour of dried blood, with no atmosphere and no pretense of hospitality. Each of these worlds looks exactly as dangerous as it is. Your eyes, your instincts, your pattern recognition hardware, the millions of years of evolutionary wiring that kept your ancestors alive on the African savanna, all tell you the same thing when you look at these places. This is wrong. This is not home. Do not relax. Titan does the opposite. Titan tells you to relax. And that is what makes it the most psychologically dangerous world a human being could ever set foot on. The reason is structural, not accidental. Titan is the only world beyond Earth where the surface environment operates through the same fundamental physical processes that shape our planet: evaporation, condensation, precipitation, runoff, erosion, deposition, wind transport, seasonal cycling. These are not superficial resemblances. They are deep mechanical parallels, the same thermodynamics, the same fluid dynamics, the same interactions between a volatile substance and a solid surface under the influence of gravity and solar energy. On Earth, the volatile is water. On Titan, it is methane. but the machinery is identical. The same equations govern both systems. The same patterns emerge, and those patterns produce landscapes that look, to a human brain trained on a lifetime of earthly experience, overwhelmingly familiar. This is not a coincidence. It is a consequence of physics. When you have a volatile substance near its triple point on a world with a substantial atmosphere, you get a weather cycle. When you have a weather cycle, you get clouds. When you have clouds, you get rain. When you have rain falling on solid terrain under gravity, you get rivers. When rivers reach low-lying areas, you get lakes and seas. When wind blows across loose particulate material, you get dunes. These are not Earth-specific outcomes. They are physics-specific outcomes, and they will emerge on any world where the right conditions exist, regardless of what the volatile substance is. Titan proves that. It runs the entire hydrological playbook with a completely different molecule and arrives at a landscape that a geologist could map using the same terminology and the same classification systems developed for Earth. And that is exactly the problem, because the human brain does not evaluate environments molecule by molecule. It evaluates them by pattern. Rain means water means drinkable. Clouds mean weather, means familiar. Shoreline means coast means approachable. Thick air means atmosphere means breathable. These associations are not conscious decisions. They are reflexes, built into the way your visual cortex interprets spatial information and the way your limbic system assigns emotional valence to sensory inputs. You do not choose to feel that a cloudy sky with rain is less threatening than a black vacuum with no horizon. You simply feel it. Your brain makes the assessment in milliseconds, below the level of awareness, and delivers a verdict. This place has features I recognize, therefore this place is less dangerous than the one that has none. On Titan, that verdict is a death sentence. Every survival instinct honed by evolution on a water-based world with an oxygen atmosphere becomes a liability on a methane-based world with a nitrogen atmosphere. The thick air that feels pressurized and therefore breathable is not breathable. The rain that looks like water and therefore safe is not safe. The lake that looks like a body of water and therefore navigable is not navigable by any vessel designed for water. The ground that looks like rocky terrain and therefore solid may be undermined by hydrocarbon dissolution or coated in slippery organic condensate. The overcast sky that looks like a cloudy day and therefore tolerable is actually a photochemical haze that blocks 99% of the already meager sunlight reaching Titan's orbital distance. Every signal your brain uses to assess environmental safety fires incorrectly on Titan. The place looks survivable. It is not. This is fundamentally different from the danger posed by any other hostile world humans have considered visiting or settling. On Mars, the danger is obvious and constant. The sky is a pale butterscotch colour that no earthly sky has ever been. The air is less than 1% of Earth's pressure, thin enough that twilight lingers for hours as dust scatters the last light across the horizon. The landscape is barren, rust-coloured, cratered, and desert dry in a way that goes beyond any terrestrial desert. Even the driest place on Earth, the Atacama, has microbial life in its soil. Mars does not. Nothing about Mars tricks you into thinking it is safe. Every visual cue, every atmospheric reading, every landscape feature tells you the same thing. This is not home, and you are in danger. Your instincts correctly identify it as foreign territory, and that foreignness keeps your vigilance high. The wrongness of the place is your ally. It never lets you forget where you are. On the moon, the wrongness is absolute and total. No atmosphere, no weather, no sound, no colour except grey and black and the blinding white of direct sunlight on regolith. The sky is black at all times, even with the sun blazing overhead. The horizon is sharp and close because the moon is small. Shadows are pitch dark because there is no air to scatter light into them. Nothing about the lunar surface registers as anything other than desolation. Your brain categorizes it instantly. Alien, hostile, empty. You will never be lulled into complacency on the moon because there is nothing there to lull you. Venus is so extreme that the very idea of standing on its surface barely qualifies as a thought experiment. The temperature exceeds 460 degrees Celsius, hot enough to melt lead, hot enough to glow faintly red in the dark. The atmospheric pressure is 90 times Earth's, equivalent to being 900 meters deep in an ocean. The clouds are sulfuric acid. No robotic lander has survived on Venus's surface for more than about 2 hours. A human being there is not endangered. A human being there is impossible. Europa looks like what it is, a frozen, radiation-blasted wasteland with a thin, almost non-existent atmosphere of oxygen, so sparse it might as well not exist. Its surface is scarred with reddish-brown fractures that speak of tidal stress and chemical contamination from the subsurface ocean below. Jupiter's radiation belts deliver enough ionizing radiation to the surface to kill an unshielded human in hours. Nothing about Europa says welcome. Titan says welcome, and it is lying. That sentence sounds absurd, but it captures the psychological reality of what Huygens revealed when it photographed rounded pebbles on a flat plain under an overcast sky, near what appeared to be a muddy shoreline with drainage channels visible on the surrounding highlands. Strip away the data overlays, the temperature readings, the atmospheric composition charts, and look only at the visual information. What you see is a place your brain has encountered thousands of times, a damp, pebble-strewn flat near a coastline after a storm. It is so familiar that the danger becomes invisible. An invisible danger is the most lethal kind. This has implications for any future human mission that go beyond engineering and life support. It raises a question that mission planners and psychologists will eventually need to confront directly. How do you train a human crew to remain constantly vigilant in an environment that looks safe? On every other world, the alienness of the landscape reinforces caution. Every glance out the window reminds you that you are not on Earth. On Titan, every glance out the window reinforces the illusion that you might be. The clouds look like clouds. The rain sounds like rain. The horizon has the gentle curve and muted colour of an overcast morning. The thick air carries sound the way Earth's does. You would hear things on Titan, unlike on Mars where the thin atmosphere makes sound faint and tinny, or on the Moon where silence is absolute. Titan would sound almost normal. Voices would carry, wind would whisper, equipment would hum, and all of it would create a sensory experience that nudges the brain, constantly and subtly, toward the conclusion that the environment is manageable, benign, Earth-like. Every one of those nudges would be wrong. This is the trap of resemblance. Not a metaphorical trap, a literal, cognitive hazard. A known psychological phenomenon in which familiarity reduces perceived risk, even when actual risk remains unchanged or increases. Mountain climbers experience it on routes they have climbed before. The familiar terrain breeds complacency, and complacency breeds mistakes. Pilots experience it on routine flights. The 10,000th takeoff feels less dangerous than the first, even though the physics are identical. Titan would weaponize this effect at a planetary scale. Every day, every sortie, every glance out the window would tell you this place is fine. And every day, the chemistry of the air, the temperature of the rain, the composition of the lakes, and the distance from help would remain exactly as lethal as they were on the first day. Consider what this means for the broader question of what it takes to make a world habitable. For decades, the search for potentially habitable environments, both in our solar system and around other stars, has focused on a set of criteria that Titan superficially satisfies. A thick atmosphere, surface liquids, a weather cycle, geological activity, complex chemistry, energy sources. Titan checks many of these boxes. It has an atmosphere thicker than Earth's. It has more surface liquid than any world except Earth. It has a complete and active weather cycle with clouds, rain, rivers, and seas. Its surface is geologically young and dynamic. Its chemistry is the most complex of any body in the solar system outside Earth. And yet the idea of a human actually living there, not visiting in a sealed vehicle for a few hours, but living day after day, month after month, reveals how hollow those criteria are without the right molecular context. Atmosphere means nothing if the atmosphere contains no oxygen. Surface liquid means nothing if the liquid is cryogenic methane that would freeze biological tissue on contact. A weather cycle means nothing if the rain would cause instant cryogenic burns to exposed skin. Complex chemistry means nothing if that chemistry is based on hydrocarbons and nitriles rather than water and amino acids. Geological activity means nothing if that activity involves cryovolcanic eruptions of ammonia water slurry onto a surface where the ambient temperature is nearly 200 degrees below the freezing point of water. Titan teaches us that habitability is not a checklist of structural features. It is a specific, narrow, chemically precise set of conditions that Earth happens to satisfy and that almost nowhere else in the solar system does. The presence of Earth-like processes does not create Earth-like outcomes. The machinery can be identical and the product can be lethal, because the product depends not on the machinery but on the ingredients fed into it. This lesson will become increasingly important as the next generation of space telescopes characterizes the atmospheres of rocky exoplanets orbiting other stars. When astronomers detect a world with a thick nitrogen atmosphere and evidence of surface liquids and active weather, and they will, eventually, because the universe is large enough to produce such worlds frequently, the temptation will be enormous to call it Earth-like, to rank it high on habitability indices, to speculate about life on its surface based on the presence of familiar-sounding environmental features. Titan is the cautionary tale that should accompany every such announcement. It is the proof that a world can have everything that looks like habitability, every structural marker, every process-level similarity, every feature that fires the pattern recognition centers of the human brain, and still be one of the most hostile environments imaginable for anything alive as we understand life. The phrase Earth-like needs to be used with extreme precision and extreme care. Earth-like in process is not Earth-like in chemistry. Earth-like in structure is not Earth-like in survivability. Earth-like in appearance is not Earth-like in reality. Titan is the most Earth-like world in the solar system by nearly every structural and process level metric available. It is also a world where an unprotected human would be dead in under a minute. And yet, despite all of this, despite the killing cold, the unbreathable air, the cryogenic rain, the hydrocarbon lakes, the toxic organic haze, the dim light, the impossible distance, Titan remains one of the most scientifically compelling destinations in the solar system, not despite its alien chemistry. Because of it, the very features that make Titan hostile to human life make it invaluable for understanding how life begins. Titan is running a planetary-scale experiment in prebiotic chemistry, an experiment that has been underway for billions of years, using energy from the Sun and from Saturn's magnetosphere to drive complex organic synthesis in an atmosphere that produces tholins, nitriles, and polycyclic aromatic hydrocarbons and deposits them on a surface made of water ice. The 2025 vesicle research showed that even the formation of cell-like compartments, a step that on Earth is considered essential to the origin of life, may be possible in Titan's methane lakes, using non-water chemistry. The subsurface, even without a global ocean, may contain pockets of liquid water where that organic material could interact with a water solvent, creating conditions that resemble what scientists believe existed on early Earth before biology emerged. Titan is, in effect, a laboratory for the question that matters most in all of astrobiology. Is life an inevitable consequence of complex chemistry, given enough time and the right environment? Or is it a singular, unrepeatable event that happened once on Earth through a chain of accidents, so improbable it may never occur again? If Dragonfly finds evidence that prebiotic chemistry has advanced further on Titan than simple atmospheric photochemistry can explain, if amphiphilic molecules are organizing into membrane-like structures in the surface material, if catalytic cycles are operating in the organic-coated ice, if the chemistry shows signatures of the kind of molecular self-organization that on Earth led eventually to RNA, metabolism, and the first protocells, then the implications would reshape biology, chemistry, and philosophy simultaneously. It would mean that the pathway toward life is not unique to water, not unique to Earth's comfortable temperature range, not unique to our particular chemical environment with its oxygen and carbon dioxide and liquid oceans. It would mean the universe is more fertile, more creative, and more inclined toward complexity than even the most optimistic astrobiologists have dared to argue. And none of that would make Titan a good place to live. This is the paradox that sits at the heart of this entire story. The world that is most valuable for studying the origins of life is one of the least suitable for sustaining it. The chemistry that makes Titan a prebiotic laboratory is the same chemistry that makes it a survival nightmare. The methane that creates the weather creates the poison. The organic haze that deposits the fascinating tholins also coats every surface in contamination. The thick atmosphere that enables flight and makes pressure convenient also accelerates heat loss to a lethal degree. The low gravity that makes movement easier also means weaker bones and muscles over time for any crew that stays too long. Everything Titan offers with one hand, it takes away with the other. A crew stationed on Titan would live inside a sealed, heated, artificially lit habitat, surrounded by a landscape that looks tantalizingly like home and is chemically nothing like it. They would eat reconstituted or preserved food shipped from Earth years before their arrival. They would breathe oxygen manufactured from melted water ice using power drawn from a nuclear reactor humming somewhere beneath the floor. They would exercise on machines to slow the bone and muscle loss caused by Titan's weak gravity. They would work in shifts, sleep in bunks, maintain equipment, run experiments, and file reports that would take over an hour to reach the nearest human ear and over 2 hours to receive a response. And when they looked out windows at orange clouds drifting over dark hydrocarbon seas, they would feel the deep, primal pull of recognition. The clouds look like clouds, the shore looks like shore, the rain sounds like rain. That pull would be constant. It would not diminish with time. If anything, it would intensify, because the human mind seeks comfort in familiar patterns, and the longer you live in a place, the more your brain normalizes what it sees. A crew member who has been on Titan for a year would find it harder, not easier, to maintain the constant alertness that survival demands. The landscape would have become background. The orange sky would feel normal. The methane rain would sound routine. And that normalization, that quiet, insidious erosion of vigilance would be the most dangerous process on the entire moon. More dangerous than the cold. More dangerous than the chemistry. Because the cold and the chemistry are constant and predictable, complacency is neither. And beyond the windows, beyond the habitat, beyond the suit and the airlock and the heating system and the oxygen supply, the landscape would go about its business with complete and absolute indifference to human presence. Methane would evaporate from Kraken Marai and rise invisibly into the haze layer above. Clouds would coalesce over the northern seas in patterns driven by seasonal shifts in atmospheric circulation. Rain would fall sometimes gently, sometimes in the torrential downpours that models predict during equinox transition storms, and feed the rivers that have been cutting channels into Titan's ice crust for longer than complex life has existed on Earth. Tholins would drift down through the atmosphere in their slow, perpetual descent, each particle a tiny package of organic chemistry assembled in the upper atmosphere by ultraviolet light and delivered to the surface by gravity, adding another imperceptible layer to the coating that covers everything. The dunes would shift grain by grain in the faint equatorial wind, rearranging themselves over timescales too slow for a human eye to notice but fast enough for Cassini's radar to detect changes between flybys. Saturn would hang in the sky, enormous and banded in pale golden cream, its rings a thin, bright line visible edge-on, present on the rare occasions when the haze thinned enough to see through to the sky beyond. And the light, that perpetual, amber, gloomy twilight would never change. No dawn breaking over the horizon, no true darkness falling to reveal stars, just an endless, dim, orange half-light, as though the world existed permanently suspended in the last few minutes before nightfall, and nightfall never came. Nothing about that landscape would care whether humans survived on it or not. The methane cycle would continue, the chemistry would proceed, the tholins would accumulate, the seas would fill and empty with the seasons over decades and centuries. Titan has been doing this for billions of years and will continue for billions more, regardless of whether anyone is watching. The Dragonfly rotorcraft will arrive in 2034 and become the first machine to truly explore this world from the surface, hopping between sites, drilling into the organic coated ice, tasting the chemistry molecule by molecule. What it finds will answer questions that have haunted planetary science for decades, but it will not change the fundamental nature of the place. Titan will remain what it has always been, a world that runs Earth's playbook with the wrong ingredients. A world with weather that kills, a world with rain that burns, a world with seas that no one can swim in, a world with air that no one can breathe, a world that is close enough to home to fool your eyes and far enough from home to end your life. If humanity ever sends people to Titan, and the scientific reasons to do so are among the most compelling in all of planetary exploration, those people will live inside machines. They will eat stored food, breathe manufactured oxygen, drink melted ice, and stay warm using nuclear heat. They will venture outside in cumbersome suits for carefully timed excursions, returning coated in organic residue that must be cleaned before they can re-enter their living space. They will communicate with Earth across a delay so long that every conversation becomes a series of monologues separated by hours of silence. They will look out at a world that resembles a cold, cloudy coast on Earth and remind themselves every single day that the resemblance is a lie. And here is the final, unsettling truth about Titan, the one that makes it unlike any other destination in the solar system, the one that sits beneath all the temperature data and atmospheric models and chemical analyses like a stone at the bottom of a methane lake. Titan is not terrifying because it is completely alien. If it were completely alien, if it were a featureless ice ball, a radiation-scorched rock, a howling gas giant with no surface to stand on, it would be easy to dismiss. It would be obviously impossible, obviously inhospitable, obviously not a place for humans. Your brain would look at it, classify it as foreign, and move on. The fear would be simple and clean. But Titan is not completely alien. It is almost familiar. It has clouds. It has rain. It has rivers and lakes and seas with real shorelines and real tides. It has dunes shaped by wind. It has weather that follows the same rules as weather on Earth. It has an atmosphere you can feel against your skin. It has a surface you can stand on without a pressurized suit. It has sound. It has seasons. It has horizons and landscapes and terrain features that your brain can parse and categorize and understand, using every framework you developed growing up on a planet with water and oxygen and warmth. And every single one of those familiar things has been rewritten. The clouds are methane. The rain is liquid fuel. The rivers carry cryogenic hydrocarbons. The lakes are pools of liquefied natural gas. The seas would swallow a boat designed for water. The dunes are organic soot. The air is thick, heavy, and contains nothing you can breathe. The ground is frozen water behaving as stone. The haze is photochemical smog that coats everything in toxic organic residue. The light is a permanent amber gloom that never lifts. The temperature is so far below anything in human experience that the concept of cold becomes meaningless. And the nearest human help, even traveling at the ultimate speed limit of the universe, is more than an hour away in one direction and more than an hour back. Titan is the world that looks most like a place where you could imagine living. And that is exactly what makes it the most unsettling place in the solar system. Not the cold, not the chemistry, not the distance, the resemblance. The slow, creeping, insidious resemblance to home the clouds, the rain, the shore, the thick air, the sound of wind, the curve of a familiar horizon, all of it whispering that this place is fine, that this place is manageable, that this place is almost Earth. It is not Earth. It is Titan. And the difference between almost and actually is measured in molecules of oxygen that are not there, in degrees of warmth that do not exist, in a chemistry that has taken every process you associate with life and comfort and safety and rebuilt it from ingredients that would end you. That is what living on Titan would actually be like. Not a grand adventure on a strange new world, a slow, grinding, perpetual negotiation with a place that looks like it should let you live and has no intention of doing so. A world where survival is not a challenge you overcome once and then relax. A world where survival is the activity, every hour, every day, forever. Because the moment you stop actively surviving, the moment you trust what you see instead of what you know, Titan collects. The clouds are not water. The rain is not water. The rivers are not water. The lakes are not water. The air is not breathable. The ground is not rock. The light is not enough. And home is not close. Titan is waiting. It has been waiting for 4.5 billion years. It does not care whether you come. And if you do, it will look exactly like somewhere you could live. It is not.